There is a planet in our solar system that rotates almost completely on its side. Its magnetic field does not come from where it should. Its seasons last 21 years each, and for decades, one entire hemisphere faces the sun while the other faces nothing but void. When the only spacecraft ever sent there arrived in 1986, it recorded radiation levels so extreme that scientists could not explain them for nearly 40 years. And in 2025, researchers discovered that everything we thought we knew about what this planet is made of might be wrong. It's not Jupiter. It is not Saturn. It is the planet most people only know as a punchline. And it may be the single strangest world orbiting our star. If you enjoy the kind of science that makes you rethink what you thought you already knew, a like and a subscribe genuinely helps this channel keep going. We put a lot of care into these videos, and your support means more than you might realize. Now, are you comfortable? Let's begin. Let us get the name out of the way. You already thought about it. The moment you hear the title, the moment someone said the word out loud, a part of your brain checked out. It happened automatically. You did not choose it. It is a reflex that has been trained into almost every English-speaking person on the planet since childhood. The seventh world from the sun has a name that sounds, to modern ears, like the setup to a joke that never needed a punchline. And that accident of language has done something remarkable. It has turned one of the most genuinely alien objects in the solar system into the single most dismissed planet orbiting our star. That is not an exaggeration. Think about the planets you can picture. Mars has rovers, red dust, sunsets that turn the sky blue. Jupiter has the great red spot, radiation belts, a moon with a subsurface ocean. Saturn has the rings, the hexagonal polar storm, Titan with its methane lakes. Even Mercury and Venus carry a certain seriousness in people's imaginations. They are hostile, sure, but they are hostile in ways that feel appropriately dramatic. Uranus gets none of that. In most people's mental model of the solar system, it sits somewhere between Neptune and nothing. A pale blue circle in a textbook diagram. A world whose only widely known fact is that it rotates on its side, which sounds interesting for about 4 seconds before the conversation moves on. There is no cultural weight attached to Uranus, no blockbuster films set in its orbit, no famous image burned into the public consciousness the way Saturn's rings or Jupiter's storms have been. Ask someone to name 3 facts about Uranus, and most people will struggle to get past the tilt and the colour. And that absence of attention has created a blind spot so large that most people have no idea what they are actually ignoring. Uranus is not small. It is not marginal. It is not a frozen pebble drifting in the outer dark. It is the 3rd largest planet in the solar system by diameter, roughly 4 times wider than Earth. If you could hollow it out, you could fit 63 Earths inside it. Its mass is over 14 times Earth's mass. It has a ring system. It has 29 known moons as of 2025. It has an atmosphere, a magnetosphere, weather, seasons, and an interior that scientists are still arguing about in peer-reviewed journals right now. It is a giant planet by every meaningful definition, and yet in the hierarchy of human attention, it ranks below objects a fraction of its size. Part of the reason is distance. Uranus orbits roughly 1.8 billion miles from the Sun, about 19 times farther out than Earth. At that distance, light from our star takes approximately 2 hours and 40 minutes to reach it. The planet is so far away that it is invisible to the naked eye under most conditions. Though under perfect skies, it sits right at the edge of what human vision can detect. For most of recorded history, nobody knew it was there at all. That changes on the night of March 13th, 1781. A man named William Herschel was conducting a systematic survey of the sky from the garden of his home in Bath, England. Herschel was not a professional astronomer by training. He was a musician, a composer and organist who had emigrated from Hanover in what is now Germany. But he had developed an obsessive interest in building telescopes, grinding his own mirrors, and cataloguing the stars with a rigor that exceeded many professionals of his era. His sister, Caroline Herschel, assisted him in nearly every observation, recording data while he worked the eyepiece through freezing English nights. On that particular evening, Herschel noticed an object that did not behave like a star. It showed a visible disk rather than a point of light. Over subsequent nights, it moved against the background of fixed stars. He initially reported it as a comet. Other astronomers tracked its orbit, ran the calculations, and arrived at a conclusion that stunned the scientific world. It was not a comet. It was a planet. A new planet. The first planet discovered in recorded human history. That last sentence deserves more weight than it usually receives. Every planet known before that night, Mercury, Venus, Mars, Jupiter, and Saturn, had been visible in the sky since before humans could write. They were named by ancient civilizations. They were woven into mythology and religion. For thousands of years, across every culture that practiced astronomy, from Babylon to Greece to the Islamic Golden Age to Renaissance Europe, the inventory of planets was fixed. 5 wandering stars, plus the sun and the moon, moving against a backdrop of fixed points. The number was settled. It had been settled for so long that it felt like a fact about the universe, rather than a limitation of human eyesight. The discovery of Uranus shattered that assumption overnight. It was not simply the addition of a 7th planet to a list. It was the realization that the list had never been complete, that the solar system was larger than humanity had known for its entire history, that there could be worlds out there, orbiting the same star, obeying the same laws of gravity, that nobody had noticed. The philosophical shock was enormous. If a planet had been hiding in plain sight for all of recorded history, what else was out there? What else had been missed? The discovery opened a door that could never be closed. Within decades, astronomers would find the first asteroids, then Neptune, then Pluto, then the Kuiper Belt, then thousands of objects beyond. The modern understanding of the solar system as a vast, layered, still incompletely mapped system begins, in a very real sense, with Herschel's backyard telescope and a smudge of light that moved when it should not have. Herschel, eager to gain royal favour, initially proposed naming it Georgium Sidus, the Georgian star, after King George III of England. The name didn't stick outside Britain. German astronomer Johann Bode suggested Uranus, the Greek god of the sky and father of Saturn in classical mythology. The name followed the convention of the other planets being named after ancient deities. It was adopted internationally. And for roughly 2 centuries, nobody thought twice about how it sounded in English. By the time schoolyard humour caught up with the name, the damage to the planet's reputation was already done for an entirely different reason. Uranus is boring to look at. When Voyager 2, the only spacecraft ever to visit the Uranian system, arrived on January 24th, 1986, after a journey of more than 8 years across the outer solar system, the images it sent back were profoundly anticlimactic. Scientists had spent years preparing. The flyby window lasted only about 5.5 hours at closest approach. Instruments were configured to capture as much data as possible in a vanishingly brief encounter. And what appeared on the monitors was a nearly featureless pale blue-green sphere. Almost no cloud bands, almost no visible storms, no swirling vortices, no dramatic atmospheric structure of the kind that had made Jupiter and Saturn look like churning cauldrons of colour. Uranus looked, to a public that had grown accustomed to the visual spectacle of the other giant planets, like a smooth billiard ball floating in the dark. That single visual impression cemented a public narrative that has persisted for 4 decades. Uranus is the boring one, the quiet one, the planet with nothing going on. And because first impressions are nearly impossible to override, especially visual ones, that narrative has barely budged despite decades of subsequent evidence to the contrary. Here is the detail that almost nobody outside planetary science knows. That featureless appearance was not a permanent characteristic of the planet. It was a seasonal artifact. Voyager 2 arrived during southern summer solstice, when one pole was pointed almost directly at the sun and the other faced deep space. The atmospheric circulation pattern during solstice is fundamentally different from what the planet exhibits at other points in its orbit. Scientists did not fully understand this at the time. The visual blandness was real, but it was a snapshot of a specific moment in an 84-year cycle, not a portrait of what Uranus always looks like. As the planet moved toward its equinox in 2007, ground-based telescopes and the Hubble Space Telescope began detecting cloud bands, bright storm features, and atmospheric activity that had been virtually absent during the Voyager era. The planet had woken up. Or more accurately, the geometry of sunlight hitting its atmosphere had shifted enough to change the circulation patterns and make previously invisible structures detectable. Uranus had weather all along. It simply was not performing for the camera on the one afternoon humanity showed up. This is a recurring theme with Uranus, and one of the reasons it deserves more attention than it receives. Nearly everything we think we know about this planet is based on a catastrophically small dataset. One flyby. A few hours of close observation. A snapshot taken under conditions we now know were atypical. And from that sliver of evidence, an entire planet was written off as uninteresting. Consider what we have sent to other worlds. Mars has been visited by dozens of orbiters, landers, and rovers across multiple decades. Jupiter has been studied by Pioneer, Voyager, Galileo, Juno, and soon Europa Clipper. Saturn had the Cassini mission orbiting it for 13 years, returning hundreds of thousands of images and transforming our understanding of the ringed giant and its moons. Even distant Pluto, which is not a planet by current classification, received a dedicated flyby from New Horizons that produced a scientific revolution in our understanding of the outer solar system. Uranus has received 5.5 hours. That is it. 5.5 hours of close data from a spacecraft designed in the 1970s, launched in 1977, running on instruments less powerful than what sits in a modern smartphone. Everything else we know about Uranus comes from ground-based telescopes, space telescopes like Hubble and James Webb, and theoretical models built on the thin foundation that Voyager 2 left behind. And here is what makes the situation even more striking. Those limited tools have already revealed a planet so physically strange that it challenges fundamental assumptions about how giant planets work. Every time a better instrument is pointed at Uranus, something unexpected shows up. Not minor anomalies, not small deviations from prediction. Fundamental surprises that force scientists to revise what they thought they understood. The James Webb Space Telescope has observed Uranus multiple times since becoming operational, and each observation has produced results that deepen the mystery. In February 2025, a Webb survey discovered a previously unknown moon orbiting the planet, a tiny object roughly 6 miles across that Voyager 2 had completely missed, bringing the known satellite count to 29. In 2025 and 2026, Webb mapped the vertical structure of Uranus's ionosphere for the first time in history, revealing temperature peaks, ion density profiles, and auroral features that did not match the predictions of existing models. The planet's upper atmosphere has been cooling for decades, and nobody is entirely certain why. Meanwhile, a separate study published in late 2025 reanalyzed the Voyager 2 radiation data and concluded that the spacecraft had likely arrived at Uranus during a rare and intense solar wind event. A co-rotating interaction region that temporarily supercharged the planet's radiation belts to levels far beyond what the Uranian system normally sustains. This means that one of the most dramatic measurements from the only close encounter we have ever had was probably not representative of the planet's typical state. We caught Uranus on an unusual day, and we have been interpreting that unusual day as normal for almost 40 years. Every layer of this planet resists easy understanding. Its atmosphere, when you actually study it instead of glancing at a photograph, contains hydrogen sulfide in the upper cloud layers, which means the clouds of Uranus literally smell like rotten eggs. This is chemically distinct from the ammonia-dominated upper clouds of Jupiter and Saturn, and tells scientists something important about the temperature and pressure conditions where Uranus's clouds form. It is not a trivial detail. It is a compositional fingerprint that separates Uranus from its larger cousins in ways that matter for understanding how the outer planets formed and evolved. The ring system, though far fainter than Saturn's, has its own peculiarities. The rings of Uranus were not discovered until 1977, when astronomers watching the planet pass in front of a distant star noticed the starlight dimming briefly before and after the planet itself blocked it. The rings are narrow, dark, and separated by wide gaps. Their composition is different from Saturn's bright, icy rings. They are made of darker material and are thought to be relatively young in geological terms, possibly the debris of moons that were shattered by impacts or torn apart by tidal forces. Webb has since imaged the rings in unprecedented detail, revealing structure and brightness variations that ground-based telescopes could not resolve. The moons of Uranus are another underappreciated wonder. The 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, were the primary targets of Voyager 2's cameras during the flyby. Miranda in particular stunned scientists. It is tiny, only about 290 miles across, but its surface looked like it had been broken apart and reassembled. Massive cliff faces, some of the tallest in the solar system, cut across terrain that mixed young and ancient geological features in ways that defied straightforward explanation. The most dramatic of those cliff faces is a feature called Ve-Roh Na Ru Peas. It is a sheer escarpment estimated at roughly 12 kilometers tall, approximately 7 miles. To place that in proportion, the Grand Canyon is approximately 1 mile deep. The tallest sea cliffs on Earth, on the coast of the Hawaiian island of Molokai, reach roughly 3,000 feet. Ve Rho H Naru Ps dwarfs every vertical surface on Earth by an order of magnitude. On a world with Miranda's weak gravity, an object dropped from the top of that cliff would take roughly 8 minutes to reach the bottom. 8 minutes of freefall on a moon barely 300 miles across. The feature is so extreme and so unexpected on a tiny frozen satellite that it became one of the most reproduced images from the entire Voyager 2 mission. A jagged scar on a world that had no business being geologically interesting, but turned out to be one of the most visually arresting objects in the outer solar system. One theory proposed that Miranda had been shattered by a catastrophic impact and then gravitationally reassembled, its fragments falling back together in a disordered jumble. More recent thinking favors internal geological processes driven by tidal heating, but the surface remains one of the most visually dramatic and least understood landscapes in the outer solar system. And beyond the moons, beyond the rings, beyond the clouds, there is the planet itself. The bulk of Uranus, the interior, the part we cannot see, cannot directly sample, and as of 2025, cannot even agree on what it is made of. For decades, Uranus and Neptune were classified as ice giants, a term meant to distinguish them from the gas giants Jupiter and Saturn. The idea was that while Jupiter and Saturn are mostly hydrogen and helium with relatively small cores, Uranus and Neptune are dominated by heavier materials, specifically water, ammonia, and methane ices compressed under enormous pressure into exotic states of matter deep within their interiors. That classification became standard. It appeared in textbooks, in NASA materials, in virtually every description of the outer solar system. Then, in December 2025, a team from the University of Zurich published a study that pulled the rug out from under the entire framework. Using a new modeling approach that did not assume in advance what the interior should be made of, they showed that the available data is equally consistent with Uranus being rock-dominated rather than ice-dominated. The planet could be mostly water. It could be mostly rock. The current measurements cannot distinguish between these two fundamentally different possibilities. The label ice giant, the researchers argued, is not so much wrong as it is unjustified. We simply do not have enough information to know what Uranus is made of at the most basic level. That is an extraordinary statement about a planet in our own solar system. We can characterize the atmospheres of worlds hundreds of light years away using the James Webb Space Telescope. We can map the surface chemistry of Pluto from 4 billion miles away. But we cannot tell whether the seventh planet from our own star is made primarily of ice or rock. The uncertainty is not a gap in the margins. It is a gap at the center of the question. This is the planet that most people skip past. This is the world that gets a smirk and a shrug. A giant planet with 29 moons, and a ring system, and an atmosphere that smells like rotten eggs, and seasons that last 2 decades, and a magnetic field that comes out sideways, and an interior that might be made of rock or might be made of exotic high-pressure ice. And we have no way to tell. A planet visited once for a few hours, under abnormal conditions, by a spacecraft older than most of the scientists now studying the data it returned. And everything described so far is just the surface layer of what makes Uranus strange. The truly bizarre features, the ones that stop planetary scientists mid-sentence, lie deeper. They involve the tilt. Not just the fact that Uranus is tilted, but what that tilt does to the planet's seasons, its magnetic geometry, its energy budget, and the very meaning of what it is to be a planet in an orderly solar system. Because Uranus is not simply tilted, it is rolled almost completely onto its side. And the consequences of that single fact cascade through every physical system the planet has, producing effects so unusual that no other world in our solar system comes close to replicating them. What caused that tilt? What it means for the planet's history? And why it turns Uranus into the most structurally wrong planet we have ever studied is where the story goes next. Every planet in the solar system is tilted. Earth leans at about 23.5 degrees from vertical. That modest angle is the reason seasons exist. It is the reason summer and winter happen, why days grow longer and shorter across the year, why the Arctic has a midnight sun, and the Antarctic has polar night. 23.5 degrees. That is enough to produce every seasonal phenomenon you have ever experienced. Every harvest cycle, every monsoon, every migration pattern, every winter storm and summer drought in human history traces back to that single number. Mars tilts at roughly 25 degrees, Saturn at about 27, Jupiter barely tilts at all, just 3 degrees off vertical, which is why Jupiter essentially has no seasons worth mentioning. Neptune sits at about 28 degrees, similar enough to Earth that its seasonal cycle, while stretched across a much longer orbit, follows a broadly recognizable pattern. These are normal numbers. These are the tilts of well-behaved planets, worlds where the axis points more or less in the same general direction as the orbit, where the poles face roughly toward the top and bottom, and where sunlight arrives in patterns that make intuitive sense. Uranus tilts at approximately 98 degrees. That number needs a moment to register. It does not mean Uranus is slightly more tilted than the others. It means Uranus has gone past perpendicular. Its axis does not point up. It does not point sideways. It points slightly past sideways, almost directly along the plane of its orbit. The planet does not spin like a top. It rolls like a ball. If you could watch Uranus orbit the sun from above, you would see a world moving forward with one pole aimed almost directly at the star, then slowly rotating through its 84-year orbit until the opposite pole faces sunward, then continuing the circuit. No other planet does this. Venus rotates in the opposite direction from most planets, which is strange in its own right, but its axis is still roughly vertical. Uranus is the only major planet in the solar system whose rotation axis lies nearly in the plane of its orbit. And the consequences of that geometry are so extreme that they turn almost every normal planetary process into something unrecognizable. Start with the most basic consequence. Sunlight. On a normally tilted planet, the equator receives the most consistent sunlight across the year. The poles get less. Seasons vary, but every part of the surface receives some sunlight and some darkness on a daily basis throughout most of the year. The day-night cycle dominates, even in Earth's polar regions, where the sun stays below the horizon for months during winter. The periods of total darkness are bounded. They end. The sun comes back. On Uranus during solstice, one pole faces the sun almost directly. That pole and its surrounding hemisphere are bathed in continuous sunlight for decades. Not days, not weeks, decades. Roughly 21 Earth years of unbroken daylight for the sunward pole. Meanwhile, the opposite hemisphere faces away from the sun entirely. It sits in continuous darkness for the same 21 years. Not twilight, not dim light filtered through atmosphere. The sun simply does not appear above the horizon for a generation of Earth time. Then, the planet continues along its orbit. The geometry shifts. As Uranus approaches equinox, the Sun moves toward the equatorial plane, and for a period of time, something closer to a normal day-night cycle briefly occurs across the whole planet. The equator sees the Sun rise and set. The poles experience rapid transitions between light and dark. For a short window in its 84-year orbit, Uranus almost behaves like a regular planet. Then equinox passes and the other pole begins its long turn toward the Sun. The entire pattern reverses. The hemisphere that spent 2 decades in darkness now enters 2 decades of light. The hemisphere that basked in sunlight plunges into night, and the cycle continues, slow and relentless, each season lasting longer than most human careers. This is not a minor astronomical curiosity. It fundamentally changes how energy moves through the planet's atmosphere. On a normally tilted world, the equator is the primary driver of atmospheric circulation. It receives the most solar energy, heats up, and drives convection patterns that transport heat toward the poles. The result is the familiar banded structure visible on Jupiter and Saturn, stripes of cloud running parallel to the equator, driven by jets and circulation cells that are rooted in equatorial heating. On Uranus, during solstice, the pole receives more direct sunlight than the equator does. The energy input is inverted compared to a normal planet. The warmest point on the planet is not the equator, it is the pole aimed at the Sun. And yet, remarkably, temperature measurements show that the equator of Uranus is not dramatically colder than the sunlit pole. Heat is being redistributed across the planet with extraordinary efficiency through mechanisms that atmospheric scientists are still working to fully explain. This redistribution is one of the quiet mysteries of Uranus. The atmosphere should, by naive expectation, show enormous temperature contrast between the sunlit and dark hemispheres. It does not. Something within the atmospheric circulation is smoothing out those differences, moving energy from the bright hemisphere to the dark hemisphere, across distances of tens of thousands of miles. The atmosphere is doing work, real physical work, that the featureless appearance of the Voyager 2 photographs completely concealed. And this is where the timing of the Voyager flyby becomes critical to understanding how badly the planet was misread. Voyager 2 arrived at Uranus in January 1986, during the southern summer solstice. The South Pole was pointed almost directly at the Sun. The spacecraft approached from the sunlit side, meaning it saw the hemisphere that had been in continuous daylight for roughly 2 decades. That hemisphere, baked in steady sunlight for 21 years with no day-night cycle to drive rapid convective changes, showed almost no visible cloud structure. The atmosphere looked calm, smooth, dead. The conclusion drawn at the time was understandable. Uranus appeared to be an atmospherically inactive planet, a world where nothing much happened. Compared with Jupiter's roiling storms and Saturn's high-speed jet streams, Uranus looked like a planet that had given up. That conclusion was wrong. It was wrong because it mistook a seasonal extreme for a permanent condition. It was like visiting Antarctica in the middle of winter and concluding that the Earth has no plant life. As the years passed and Uranus moved toward its equinox in 2007, the evidence began piling up. And it did not arrive as a single dramatic announcement. It arrived in stages, each one more striking than the last, building a case that the Voyager portrait of Uranus was not just incomplete, but actively misleading. The first hints came from the Hubble Space Telescope in the late 1990s and early 2000s. Hubble's cameras, sharper and more sensitive than anything available during the Voyager era, began detecting faint banded structures in the upper atmosphere. Cloud features that had been invisible to Voyager started to appear, initially dim and tentative, as if the planet was slowly waking from a long sleep. As the planet moved closer to equinox, and the sun began to illuminate lower latitudes more directly, the changes accelerated. By 2004 and 2005, Hubble was recording bright cloud features at mid-latitudes that rivaled anything seen on Neptune. Then came the ground-based revolution. The twin Keck telescopes on Mauna Kea in Hawaii, equipped with adaptive optic systems that compensate for the blurring effects of Earth's atmosphere, achieved angular resolution comparable to Hubble and sometimes better in the infrared. When Keck turned its instruments to Uranus in the years surrounding equinox, the results stunned the community. The planet was covered in atmospheric activity. Bright convective cloud systems appeared at multiple latitudes. Dark spots, reminiscent of Neptune's Great Dark Spot but unique in their behavior, formed and dissipated on timescales of weeks to months. Banded cloud structures emerged in the lower atmosphere, visible in infrared wavelengths that penetrate deeper than visible light. The atmosphere of Uranus was not just active, it was dynamic in ways that the Voyager data had given no reason to expect. The 2007 equinox itself was a landmark moment. For the first time in 42 years, the sun crossed the equatorial plane and both hemispheres began receiving comparable illumination. The atmospheric response was rapid and dramatic. Scientists observed an asymmetry in the cloud patterns, with the northern hemisphere emerging from decades of darkness, developing more vigorous convective activity than the southern hemisphere, which was entering its long twilight. This asymmetry was not predicted by the simplest models, which assumed the atmosphere would respond symmetrically to symmetric illumination. Something about the internal state of each hemisphere, the accumulated effects of decades of darkness versus decades of sunlight, created different starting conditions that produced different atmospheric behaviors even under identical lighting. The most remarkable episode came in 2014 when a cluster of extremely bright storms erupted in the northern mid-latitudes. These storms were so large and so reflective that they were detected not just by professional observatories, but by amateur astronomers using telescopes in their backyards. A cloud feature visible on a planet nearly 2 billion miles away from a backyard telescope is an extraordinary thing. It meant the storm was reflecting enormous amounts of sunlight from a cloud top that extended well above the surrounding haze. The vertical extent of the convection driving that storm had to be substantial, reaching from deep in the atmosphere where methane could condense upward through tens of miles of atmospheric column. For a planet that had been dismissed as atmospherically dead 2 decades earlier, the sight of amateur astronomers photographing its storms from suburban driveways was a pointed rebuke to the Voyager-era narrative. What made the post-equinox atmospheric behavior scientifically important was not just the existence of storms, it was the pattern. The circulation of Uranus appeared to reorganize on a timescale tied to the seasonal cycle, shifting from a pole-dominated regime during solstice to a more equator-driven regime near equinox. The transition was not smooth. It involved bursts of convective activity, the formation and dissolution of large-scale cloud features, and changes in wind speed measurements at different latitudes. The atmosphere was not simply responding passively to changing sunlight, it was undergoing structural transitions in its circulation pattern, the atmospheric equivalent of a continent shifting from one climate regime to another. Uranus has weather, it has storms, it has wind speeds that reach up to approximately 560 miles per hour in some measurements. Not as fast as Neptune's record-breaking winds, but comparable to the most violent atmospheric flows on Saturn. The planet's atmosphere is not dead. It is cyclical on a timescale so long that a single flyby, even a well-instrumented one, captures almost nothing of the full picture. The 84-year orbit means that a full seasonal cycle has not even been completed since the planet was discovered. Herschel saw Uranus in 1781. Fewer than 3 full orbits have elapsed since then. And here's a detail that makes the seasonal picture even stranger. Uranus rotates fast. A single day on Uranus lasts only about 17 hours, shorter than a day on Earth. The planet completes a full spin before most people finish their waking hours. That means Uranus is not some sluggish world drifting slowly through its orbit. It is spinning briskly, turning on its side with a rotational energy that keeps its atmosphere in constant motion. While its seasons crawl forward across decades so long that a human born at the start of summer would reach adulthood before autumn arrived. The relationship between day and year on Uranus is broken in a way that no other planet replicates. On Earth, a year contains 365 days. On Jupiter, a year contains roughly 10,000 Jovian days. On Uranus, a single year contains more than 42,000 Uranian days. 42,000 sunrises, each one arriving from a slightly different angle as the planet inches through its orbit. Each one illuminating a slightly different slice of the tilted globe. The days are short. The seasons are immense. And the combination produces an atmospheric and thermal environment that has no analogue anywhere else in the solar system. We have never observed the planet through even one complete turn of its seasons with modern instruments. Now add the second layer of complexity, temperature. The upper atmosphere of Uranus is astonishingly cold. Measurements place the minimum temperature at roughly minus 224 degrees Celsius, or about 49 Kelvin. That is colder than the atmospheric minimum of Neptune, despite Neptune being substantially farther from the Sun. It is the coldest measured planetary atmosphere in the solar system. Colder than anything on Jupiter or Saturn. Colder than what distance alone would predict. For decades, this extreme cold was linked to another Uranian anomaly: the apparent absence of internal heat. Every other giant planet in the solar system, Jupiter, Saturn, and Neptune, radiates significantly more energy than it receives from the Sun. This excess energy comes from their interiors, left over from the heat of formation, and sustained by ongoing gravitational contraction, differentiation, or other internal processes. Jupiter radiates roughly twice the energy it absorbs. Saturn radiates roughly 1.8 times. Neptune, despite being the most distant giant, still emits approximately 2.6 times what it receives. Uranus, when Voyager 2 measured its energy budget, appeared to emit essentially no more than it absorbed. The ratio was indistinguishable from 1. This made Uranus unique among the giant planets. It seemed to have no internal heat source at all, as if the primordial warmth from its formation had somehow been lost or locked away. To understand why this was so disturbing, you have to understand the relationship between Uranus and Neptune. These two planets are not just neighbors in the outer solar system, they are near twins. Neptune is slightly more massive, roughly 17 Earth masses compared with Uranus's 14. Neptune is slightly smaller in diameter, which means it is slightly denser. But in terms of gross physical properties, size, mass, position in the outer solar system, presumed origin from similar materials in similar regions of the protoplanetary disk, Uranus and Neptune are the two most closely matched planets in our entire system. They are more alike than any other pair, more alike than Earth and Venus, more alike than Jupiter and Saturn. Planetary scientists routinely describe them as siblings, and every model of solar system formation predicts that they should have formed under broadly comparable conditions and evolved along broadly comparable paths. And yet, their thermal behavior is completely different. Neptune radiates roughly 2.6 times the energy it absorbs. Uranus appeared to radiate essentially nothing beyond what the sun provides. That is not a small discrepancy. It is as though two houses built from the same materials, on the same street in the same year, were measured in winter and one was warm while the other was ice cold inside. The first question any investigator would ask is not what is wrong with the cold house in general. It is what happened to this house specifically that did not happen to the other one. What event, what alteration, what structural difference explains why two nearly identical objects ended up in such different thermal states? That question has driven much of the theoretical work on Uranus's interior for the past 4 decades. And the answer that keeps rising to the top of the list is the one thing that obviously separates Uranus from Neptune: the tilt. Neptune tilts at a modest 28 degrees. Uranus tilts at 98. Whatever caused that tilt, whatever violence was responsible, it is the most visible difference between the two siblings. And it may be the explanation for why one of them went thermally quiet while the other did not. That measurement was the basis for one of the most stubborn mysteries in planetary science. How could a planet this massive have no detectable internal heat? Where did the energy go? Multiple hypotheses were proposed across the decades. One suggested that the giant impact that caused the tilt also disrupted the planet's internal layering, creating a compositional gradient that acts as an insulating barrier, trapping heat deep in the interior and preventing it from escaping to the atmosphere. Another proposed that the impact itself stripped away enough of the planet's primordial heat to leave it thermally depleted. A third suggested that the interior is stably stratified, meaning the material does not convect freely the way it does in Jupiter or Saturn. So heat transport from the deep interior to the surface is dramatically suppressed. Each hypothesis carried implications for what the interior looks like, what it is made of, and how the planet evolved. And for nearly 40 years, scientists operated under the assumption that the Voyager measurement was accurate and that Uranus truly was thermally silent. Then, in July 2025, a study led by researchers at the University of Houston presented a revised energy budget spanning a complete orbital period from 1946 to 2030. By combining spacecraft observations with advanced computer modeling of how Uranus absorbs and emits energy at all latitudes and all seasons, they showed that the planet does emit more heat than it absorbs, approximately 12 to 15% more. The internal heat flux is real. It is subtle, far smaller than Neptune's, but it is there. The finding overturned one of the oldest assumptions about the planet. Uranus is not thermally dead, it is thermally quiet. And the distinction matters enormously because it changes which interior models are viable and which are not. A planet with a small but detectable internal heat source is structurally different from one with no heat source at all. The insulating barrier hypothesis, for example, remains plausible, but now must be recalibrated. The interior cannot be so perfectly insulated that no heat escapes. Something gets through, but far less than on any comparable world. Far less critically than on the sibling planet that should by all rights behave the same way. The Houston study also revealed something else that connected directly back to the tilt. The energy budget of Uranus changes with its seasons. The amount of heat the planet absorbs varies significantly depending on which hemisphere is facing the sun and how directly. Over the course of an 84-year orbit, the total absorbed solar energy fluctuates in a pattern that mirrors the extreme seasonal geometry. This means the atmosphere and the uppermost layers of the interior are constantly adjusting to a changing energy input on timescales of decades, a slow pulsation of warmth and cold that has no equivalent on any other giant planet. The reason this connects back to the tilt is that the tilt itself may be responsible for the thermal strangeness. The giant impact hypothesis, the leading explanation for why Uranus is rolled onto its side, carries consequences that extend far beyond the angle of the axis. If a massive object struck Uranus during the late stages of planet formation, the energy deposited into the planet would have been enormous. But the geometry of the impact determines how that energy was distributed. A head-on collision deposits energy deep into the interior. A grazing impact deposits energy predominantly in the outer layers. Some models suggest that the impact that tilted Uranus was more grazing than head-on, which would explain two things simultaneously: the extreme tilt and the thermal deficit. A grazing impact would spin the planet sideways without delivering as much energy to the deep interior. It might also have mixed the outer layers in a way that created the compositional gradient needed to suppress convection and trap whatever internal heat remained. Neptune, having never suffered a comparable impact, would have retained its primordial heat transport mechanisms intact. Its interior convects normally, its heat escapes normally. It behaves the way a planet of its size and age should behave. Uranus does not, and the impact is the leading candidate for why. This is a hypothesis, not a confirmed fact, but it illustrates something important about how Uranus operates as a scientific puzzle. The tilt is not just an angle, it is a clue. It points backward in time to a violent event whose specific character shaped the planet's thermal evolution, its atmospheric behavior, its seasonal cycle, and possibly the structure of its interior down to the present day. One event, if it happened the way models suggest, set the conditions for almost everything we see 4.5 billion years later. The giant impact hypothesis itself deserves closer examination, because it carries a weight that most casual descriptions of Uranus skip over entirely. In the standard model of solar system formation, the giant planets formed from the gas and dust of the protoplanetary disk surrounding the young sun. Jupiter and Saturn accumulated massive hydrogen and helium envelopes early, while they could still gravitationally capture the lightest gases from the disk. Uranus and Neptune formed later or in less gas-rich regions, and ended up with smaller hydrogen-helium envelopes wrapped around denser cores of heavier material. The details remain debated, but the broad framework is well supported. Within that framework, there is nothing that would naturally produce a 98-degree tilt. Planets forming from a disk of material that all orbits in roughly the same plane should end up spinning in roughly the same direction, with axes roughly perpendicular to that plane. Small deviations are expected. the result of late-stage impacts and gravitational interactions. But 98 degrees is not a small deviation. It is a catastrophe. The most widely accepted explanation is that a body roughly 1 to 3 times the mass of Earth collided with the young Uranus at a specific angle and velocity sufficient to knock it sideways without destroying it entirely. The timing of this impact matters. If it happened early enough, while Uranus was still accumulating its atmosphere, the atmosphere would have had time to settle into the new rotational frame. If it happened later, after the atmosphere was established, the consequences would have been different and potentially more violent. Some models suggest the impact may have also created a debris disk around the tilted planet, from which some of the inner moons subsequently formed. This is not a minor footnote. It is a claim about the origin of an entire satellite system. The 5 major moons of Uranus, Miranda, Oriole, Umbriel, Titania, and Oberon all orbit in the plane of the planet's equator, tilted at the same extreme angle as Uranus itself relative to the rest of the solar system. Their orbital plane follows the tilt, not the solar system's reference frame. This alignment is one of the strongest pieces of evidence that the moons formed after the tilting event. If they had existed before the impact, their orbits would have been disrupted, scattered into inclined or eccentric paths that would not neatly align with the new equatorial plane. The fact that they do align suggests they condensed from a disk of material that was generated or reorganized by the collision itself. The inner moons, the smaller satellites that orbit closer to the planet and within the ring system, strengthen this case further. Several of them are thought to be relatively young, geologically speaking, based on their dynamical relationship with the rings and with each other. Their orbits show signs of ongoing gravitational interactions, resonances, and perturbations that suggests the inner satellite system is not a static relic from the early solar system, but an evolving population that has been created, disrupted, and reformed over time. The debris disk hypothesis provides a natural origin point for these objects. The impact generated a cloud of debris. The debris settled into a disk. The disk clumped into moons. And those moons have been interacting with each other and with the ring system ever since, producing the complex and still not fully understood architecture that Voyager 2 glimpsed during its flyby. Miranda's tortured surface fits this narrative. If Miranda formed from the collision debris, it may have assembled from materials of varying composition and thermal history, producing a world with a heterogeneous interior prone to uneven geological evolution. The massive cliff faces and jumbled terrain that Voyager photographed could be the visible consequences of a moon that was never homogeneous to begin with. A world born from wreckage and carrying the scars of its violent origin in every canyon and ridge. Other models, proposed more recently, suggest that the tilt may not have been caused by a single catastrophic blow, but by a series of smaller impacts during the chaotic final stages of planet formation. In this scenario, no single event was responsible. Instead, a sequence of collisions gradually pushed the axis further and further from vertical, with each impact contributing a fraction of the total tilt. This model avoids some of the fine-tuning problems of the single impact scenario, where the impactor's mass, speed, and angle all have to fall within a narrow range to produce the observed result. A third class of models, even more recent, proposes that gravitational interactions with other planets during a period of orbital migration could have contributed to or even dominated the tilting process. In these scenarios, the giant planets did not form in their current orbits, but migrated inward and outward during the solar system's youth, exchanging angular momentum and potentially passing through orbital resonances that excited large tilts. This framework does not necessarily eliminate the need for an impact, but suggests the impact may have been the final push on a planet that was already partially tilted by gravitational dynamics. The honest scientific picture is that we do not know which of these scenarios is correct. We know the tilt is real, we know it is extreme, we know it had to be caused by something violent or dynamically unusual, and we know that whatever caused it left the planet in a state unlike anything else in the solar system. But the tilt alone, extraordinary as it is, does not fully capture what makes Uranus strange. The tilt is the seed. The strangeness grows from it in every direction, into the seasons, the energy balance, the atmospheric circulation, and into something even harder to explain: the magnetic field. Because when Voyager 2 measured the magnetic field of Uranus, what it found was so far from any prediction, so misaligned with the planet's rotation, so offset from its center, and so structurally bizarre that it forced a complete rethinking of how planetary magnetic fields are generated. And when the James Webb Space Telescope confirmed and extended those measurements nearly 4 decades later, the picture did not get simpler. It got stranger. The interior of Uranus, the region where the magnetic field is born, the region where heat is trapped or released, the region where rock meets ice meets compressed gas under pressures that no laboratory on Earth can replicate, is where the deepest layer of planetary wrongness lives. And it is where the story goes next. On every well-studied planet in the solar system that has a global magnetic field, the field behaves in a way that makes geometric sense. The magnetic poles sit near the rotational poles. The field is roughly symmetrical, shaped like the pattern you get when you scatter iron filings around a bar magnet, with clean lines arching from one pole to the other. The axis of the magnetic field is tilted slightly from the axis of rotation, but the tilt is small. On Earth, the magnetic pole sits about 11 degrees from the geographic pole. On Jupiter, the offset is roughly 10 degrees. On Saturn, the alignment is almost perfect, less than 1 degree of separation. This is not a coincidence. It is a consequence of how planetary magnetic fields are generated. Deep inside these planets, electrically conducting fluids, liquid iron on Earth, metallic hydrogen on Jupiter and Saturn, are set into motion by convection and by the planet's rotation. The rotation organizes the flow into patterns aligned with the spin axis, and because the fluid motions generate the magnetic field through a process called the dynamo mechanism, the resulting field naturally aligns with the rotation. The closer the fluid motions are to being symmetric around the spin axis, the closer the magnetic poles are to the rotational poles. This is one of the cleanest, most intuitive relationships in planetary physics. Rotation drives the dynamo. The dynamo produces the field follows the rotation. It works on Earth. It works on Jupiter. It works on Saturn. It is the baseline expectation for any planet with a conducting interior and a reasonably fast rotation. Then there is Uranus. When Voyager 2 measured the magnetic field of Uranus in January 1986, the data defied every expectation the science team had prepared for. The magnetic axis was tilted 59 degrees from the rotation axis, not 11 degrees like Earth, not 10 like Jupiter, 59. The magnetic poles were closer to the equator than to the geographic poles. The field did not emerge symmetrically from the planet's center. It was offset, displaced from the middle of the planet by roughly a third of the way toward the surface. And the shape of the field was not a clean dipole. It was messy with strong higher order components, quadrupole and octupole terms that gave the field a lumpy, asymmetric geometry unlike anything seen on any other planet. The initial reaction in the planetary science community was cautious shock. Scientists considered the possibility that the measurement was anomalous, that Voyager 2 had passed through the magnetosphere at an unusual moment or along an unfortunate trajectory that exaggerated the apparent offset. But the data was consistent across multiple instruments, and the flyby geometry was well understood. The measurement was solid. Then, 3 years later, Voyager 2 reached Neptune and found something similar. Neptune's magnetic field is also severely tilted, about 47 degrees from the rotation axis, and offset from the planet's center by a comparable fraction. This was the confirmation that the Uranian measurement was not a fluke. Whatever was causing the magnetic weirdness at Uranus was also at work at Neptune. The ice giants, as a class, had magnetic fields that broke the rules. This double result eliminated one of the earliest proposed explanations for Uranus's magnetic offset, that the field was in the middle of a polarity reversal, a process that Earth's own magnetic field undergoes every few 100,000 years. During a reversal, Earth's field becomes temporarily disordered, with the magnetic poles wandering away from the geographic poles before settling into a new configuration. If Uranus happened to be caught mid-reversal during the Voyager flyby, the disordered field would be a transient state, not a permanent feature. But Neptune showing the same pattern made the reversal explanation implausible. The odds of catching both planets mid-reversal during the same decade-long mission were vanishingly small. The explanation that has gained the most traction over the past 3 decades is structural. On Earth, the magnetic field is generated deep in the core, in the liquid iron outer core that extends from roughly 1,800 miles below the surface to the boundary with the solid inner core at about 3,200 miles depth. On Jupiter and Saturn, the dynamo operates in the deep interior where hydrogen is compressed into a metallic state. In both cases, the dynamo region is centered on the planet's core and roughly symmetric around the spin axis. On Uranus and Neptune, the dynamo is thought to operate not in the deep core, but in a shallow shell. The conducting fluid is not metallic hydrogen or liquid iron. It is water, ammonia, and other volatile compounds compressed into an electrically conducting state at high pressures, a state sometimes called ionic water or superionic ice, depending on the specific conditions. This conducting layer sits above the rocky or mixed composition core and below the hydrogen-helium envelope. If the dynamo operates in a thin shell rather than in a deep sphere centered on the planet's core, the geometry of the resulting field changes dramatically. A thin shell dynamo naturally produces fields that are offset from the center, that have strong higher-order multipole components, and that can be tilted at large angles from the rotation axis. The models are not yet precise enough to reproduce the observed field of Uranus in detail, but they capture the general character of it. The magnetic wrongness of Uranus may not be a sign that something broke. It may be a direct reflection of where inside the planet the field is being generated. But this explanation raises as many questions as it answers. The depth, thickness, and composition of the conducting shell are not known. They depend on the interior structure, which, as we covered, is itself deeply uncertain. If Uranus is ice-rich, the conducting layer is likely a thick mantle of compressed water and ammonia that extends through a significant fraction of the planet's interior. If Uranus is rock-rich, the conducting layer is thinner, positioned differently, and composed of different materials under different pressure and temperature conditions. The two scenarios produce different dynamo geometries, different field strengths, and different predictions for how the field varies with time and location. And the December 2025 study from the University of Zurich added another dimension to this problem. Their models showed that rock-rich interior configurations can also produce multipolar, off-center magnetic fields, because the dynamo shell in a rock-dominated planet would occupy a different region with different conductivity profiles. This means the magnetic field data, which scientists had hoped might help distinguish between interior compositions, does not cleanly favor one interpretation over the other. Both rock-rich and water-rich interiors can produce the kind of messy, tilted offset field that Voyager 2 measured. The magnetic field, strange as it is, does not solve the composition puzzle. It deepens it. This is where the James Webb Space Telescope entered the picture and changed the conversation. In 2025, a team led by Henrik Melin at Northumbria University used the near-infrared spectrograph on Webb to observe Uranus's ionosphere, the charged upper layer of the atmosphere where the magnetic field leaves its fingerprints. The ionosphere glows faintly in the near-infrared, emitting light from a molecule called H3+, a positively charged form of hydrogen that is created when energetic particles from the magnetosphere or solar wind collide with hydrogen in the upper atmosphere. By mapping the distribution and intensity of this emission across the planet's disk, the team could trace where the magnetic field channels energy into the atmosphere. What they found was startling. The emission was not concentrated at the geographic poles, as it would be on Earth or Jupiter. It appeared at equatorial and mid-latitude regions, consistent with the severely tilted magnetic field, placing the magnetic poles far from the spin poles. The team identified auroral features in both the northern and southern hemispheres, but these auroras were not where any intuition about planetary auroras would place them. On Earth, the northern lights appear in rings around the Arctic and Antarctic. On Uranus, the equivalent phenomenon sweeps across latitudes that on Earth would correspond to the tropics and the temperate zones. Think about what that means for a moment. On Earth, auroras are a polar phenomenon. People travel to Iceland, Norway, or northern Canada to see them. They are associated with high latitudes, cold nights, and the magnetic funneling of charged particles into the atmosphere near the poles. If Earth's magnetic field were configured like that of Uranus, the northern lights would appear over Mexico City, Cairo, and New Delhi. The southern lights would glow over Sydney, Johannesburg, and Buenos Aires. The entire intuitive geography of magnetic interaction between a planet and its space environment would be inverted. That is what Uranus lives with as a permanent condition, not a temporary anomaly, but the baseline way its magnetosphere interacts with the solar wind and its own atmosphere. The 2025 observations also revealed a dark band in the ionospheric emission, aligned with the magnetic dip equator, the line on the planet's surface where the magnetic field runs parallel to the ground. This was the first direct detection of the magnetic field's imprint on Uranus's ionosphere. It confirmed that the tilted, offset field is not just a far-field phenomenon measurable only from space. It physically shapes the atmosphere, influencing where charged particles are deposited, where heating occurs, and where the upper atmosphere is ionized. A follow-up study published in February 2026 by Paula Tirante and colleagues took this further. Using a 15-hour continuous observation session that covered nearly a full rotation of the planet, they mapped the vertical structure of the ionosphere for the first time in history. They measured how temperature and ion density change with altitude, from the cloud tops up through thousands of miles of increasingly thin atmosphere. The results showed that temperatures peak between 3,000 and 4,000 kilometers above the planet, while ion densities peak much lower, near 1,000 kilometers. Both measurements were significantly different from what models had predicted. The ion densities were weaker than expected. The temperature structure was more complex. The temperature peak at 3,000 to 4,000 kilometers altitude is itself a puzzle that connects to a broader problem in planetary science known as the giant planet energy crisis. On every giant planet observed so far, including Jupiter, Saturn, and Neptune, the upper atmosphere is significantly hotter than it should be, based on solar heating alone. The sun simply does not deliver enough energy to the upper atmospheres of these distant worlds to explain the temperatures measured there. Some additional energy source is heating them from below or from within. And on most giant planets, the prime suspects are gravity waves propagating upward from the lower atmosphere and auroral heating from the magnetosphere. On Uranus, the mystery is compounded by the planet's unique magnetic geometry. Auroral energy is deposited at low and mid-latitudes rather than at the poles, which means the heating pattern is fundamentally different from that on any other giant planet. Yet the upper atmosphere still shows elevated temperatures. Whatever mechanism solves the energy crisis for Jupiter and Saturn may not directly apply to Uranus, because the geometry of energy input is so different. They also confirmed something that other researchers had begun to suspect from earlier data. Uranus's upper atmosphere has been cooling over the past several decades. The thermospheric temperatures measured by Webb are lower than values estimated from observations in the late 20th century. A planetary atmosphere that is slowly cooling at the top, while its deep interior retains subtle heat, is a thermodynamic puzzle that does not have a straightforward explanation. It may be related to changes in solar activity over the decades. It may be connected to the planet's extreme seasonal cycle as it moves past equinox and toward the next solstice. Or it may reflect something about the internal energy transport that we do not yet understand. The broader significance of the Webb ionosphere mapping is that it gives scientists a tool they have never had before. The magnetic field of Uranus was measured once, during a few hours in 1986, from a single trajectory through the magnetosphere. Everything since then has been inference and modeling. Webb cannot measure the magnetic field directly from its orbit around the Sun, but it can map the atmospheric effects of the field with a resolution and sensitivity that were previously impossible. Over time, repeated observations may reveal how the field varies, whether it is stable or evolving, and how the auroral patterns shift as the planet rotates and moves through its orbit. This makes Webb not just a telescope for Uranus, but a long baseline magnetic field monitor, using the ionosphere as a proxy for the invisible forces beneath it. Now turn from the magnetic field to what lies beneath it, the interior. The question of what Uranus is made of sounds like it should have been answered decades ago. We know what Earth is made of. We know the broad composition of Jupiter and Saturn. We have reasonable models for Mars and Venus, but Uranus, despite being one of the 8 major planets in our own solar system, remains compositionally ambiguous at the most fundamental level. The traditional picture established in the decades following the Voyager flyby divided Uranus into 3 layers: an outer envelope of hydrogen and helium gas, a thick middle mantle of compressed ices, primarily water, ammonia, and methane, and a small rocky core at the center. This 3-layer model fit the available data well enough. The term ice giant was coined to describe this structure, distinguishing Uranus and Neptune from the gas giants Jupiter and Saturn, where hydrogen and helium dominate the composition by mass. But the available data was never as constraining as the confidence of the label implied. The primary observational inputs are the planet's total mass, its radius, its gravitational field measured through its effect on the trajectories of ring particles and moons, and its rotation rate. From these quantities, scientists can calculate how density varies with depth and can test which combinations of materials are consistent with the observed profile. The problem is that the solution is not unique. Multiple very different interior compositions can produce the same mass, radius, and gravitational moments. This degeneracy, the technical term for when multiple solutions fit the same data equally well, is the core of the problem. And it is not a small degeneracy. As the December 2025 study by Luca Morf and Professor Ravit Hellard at the University of Zurich demonstrated, the range of possible interiors extends from models where water dominates the mantle to models where rock dominates it. The rock-to-water mass ratio consistent with current data ranges from as low as 0.04 to as high as 3.92 for Uranus. That is a factor of nearly 100 between the most water-rich and most rock-rich models that still satisfy all observational constraints. Let that range settle for a moment. We are not talking about a 10% uncertainty. We are talking about a planet that could be almost entirely water beneath its hydrogen envelope, or almost entirely rock, and we cannot currently distinguish between these two fundamentally different objects. The ice giant label assumes an answer. The data does not provide one. The Zurich team's approach was deliberately agnostic. Instead of starting from an assumed composition and checking whether it fit the data, they started from randomly generated density profiles and applied an iterative algorithm that converged toward models satisfying hydrostatic equilibrium, the observed gravitational moments, and thermodynamic consistency. The result was a wide landscape of valid solutions, spanning compositions, temperature profiles, and convective structures that previous models had ruled out by assumption rather than by evidence. One particularly striking finding involved convection. In traditional models of giant planet interiors, the deep interior is assumed to be fully convective, meaning material circulates freely from bottom to top, transporting heat efficiently. This assumption is inherited from Jupiter and Saturn, where the interiors are thought to be largely convective. But the Zurich models showed that stable, non-convective regions are not only possible within Uranus, but may be necessary to explain some observational constraints. A stably stratified interior, where material does not mix freely across layers, would suppress heat transport and could explain why the planet's internal heat flux is so much lower than Neptune's. This connects directly to the thermal mystery. If Uranus's interior is stably stratified, heat generated during formation or by ongoing processes like radioactive decay would be trapped at depth, unable to reach the surface efficiently. The planet would appear thermally cold from outside, even if its deep interior retains significant heat. The 2025 study from the University of Houston showed that a small amount of heat does escape, roughly 0.078 watts per square meter on average, but this is a tiny fraction of what an equivalent convective interior would produce. The stable stratification could also be connected to the giant impact. A massive collision would have injected energy unevenly into the planet, potentially mixing the outer layers while leaving the deep interior relatively undisturbed. Over billions of years, the mixed outer region could have developed a composition gradient, a gradual transition from hydrogen-rich gas at the top to heavier material below that acts as a barrier to convection. Fluid parcels trying to rise through this gradient encounter increasingly lighter material above them and cannot continue upward. They stall. Heat stalls with them. This scenario is physically plausible and widely discussed in the literature, but it is not confirmed. It is one possibility among several, and the fundamental problem remains. Without direct measurements of the interior, without a probe descending through the atmosphere to sample composition with depth, without an orbiter mapping the gravitational field with sufficient precision to break the degeneracy between models, the interior of Uranus remains a scientific blank. There is a further complication that makes the interior puzzle even more unsettling. The exotic states of matter that may exist inside Uranus have no analogue on Earth's surface, and are only beginning to be recreated in laboratories. At the pressures found deep within Uranus, water does not behave like water. It enters a state called superionic ice, where the oxygen atoms lock into a crystalline lattice, while the hydrogen atoms move freely through the lattice like a fluid. The result is a material that is simultaneously solid and liquid. A crystal that conducts electricity because its hydrogen nuclei carry charge as they flow. This is not theoretical. Superionic ice has been created in laboratory experiments, most notably at the National Ignition Facility at Lawrence Livermore National Laboratory, using laser-driven shock compression to replicate the pressures and temperatures found deep within ice giant interiors. The experiments work by firing an array of powerful lasers at a tiny sample of water, compressing it to millions of times atmospheric pressure in a fraction of a second, and then measuring how the material responds. The results confirmed that at pressures above roughly 1 million times sea level atmospheric pressure, water transitions into the superionic state. The oxygen lattice forms. The hydrogen becomes mobile. The material becomes an electrical conductor. The confirmation was a landmark in high-pressure physics, but it also deepened the mystery of what is actually happening inside Uranus. The conducting properties of superionic ice are different from those of liquid metallic hydrogen or liquid iron. It conducts electricity, but not in the same way or with the same efficiency. The convective properties are different. In normal water, convection involves the bulk movement of fluid, parcels of hot water rising while cooler water sinks. In superionic ice, the oxygen lattice is fixed. Only the hydrogen moves. That means convection in the traditional sense may not occur at all within a superionic layer. Heat transport would happen through a different mechanism, the diffusion of mobile hydrogen ions through a rigid crystal framework, and the rate of that transport would be dramatically lower than in a fully liquid convective layer. If a significant portion of Uranus's interior is made of superionic water, it would create a zone where heat is trapped not because of a compositional barrier, but because of the physics of the material itself. The superyonic layer would act as a thermal blanket, slowing the escape of primordial heat from the deep interior toward the surface. This provides yet another possible explanation for Uranus's thermal quietness, one that does not require a giant impact to set up an insulating gradient. The material itself, under the conditions that exist inside the planet, is naturally insulating. But the superyonic ice story comes with a critical caveat. The laboratory experiments were conducted on pure water. The interior of Uranus, whatever its composition, is not made of pure water. It is a mixture, possibly including ammonia, methane, hydrogen, helium, and silicate materials in proportions that are themselves unknown. When you add impurities to water under extreme pressure, the phase behavior changes. The temperature and pressure at which superyonic transitions occur shift. The conductivity of the resulting material changes. The crystal structure may be different. Every number derived from pure water experiments carries an uncertainty that scales with how different the real mixture is from the laboratory sample. This is the kind of problem that cannot be resolved by theory alone. It requires either dramatically more sophisticated experiments using realistic planetary mixtures under extreme conditions, or direct measurements from inside the planet. Neither of these is currently available, though both are being pursued. Laboratory groups around the world are working to extend the shock compression experiments to more complex mixtures, and the proposed Uranus orbiter and probe mission would, through its atmospheric probe and gravitational field mapping, provide the data needed to constrain which compositions are actually present at which depths. And if the interior is rock-dominated instead of ice-dominated, the superyonic story may not apply at all. The conducting fluid would be something else entirely, possibly silicate material under extreme compression, and the dynamo mechanism would operate in a different region, at different depths, with different geometry. The thermal insulation mechanism would be different. The density profile would be different. The entire physical picture of the planet's deep interior would change from the ground up. This is the core of the problem with Uranus. We are not dealing with one unknown. We are dealing with a cascade of unknowns, each of which depends on the others. The magnetic field depends on the interior structure. The interior structure depends on the composition. The composition depends on measurements we do not have. And until we get those measurements, every model of Uranus, every paper, every simulation, every textbook description is built on a foundation that could shift fundamentally with a single definitive observation. And that blank is not academic. It has consequences that extend far beyond one planet. The composition of Uranus is a benchmark for understanding an entire class of worlds. Among the thousands of exoplanets discovered over the past 3 decades, the most common type of planet in the galaxy is not a gas giant like Jupiter or a rocky world like Earth. It is something in between. Sub-Neptune and super-Earth-sized planets, worlds with radii roughly 2 to 4 times Earth's, appear around other stars with a frequency that dwarfs every other planetary category. They are the default planet of the Milky Way, and we have no close analogue for them in our solar system except Uranus and Neptune. Every model of what these exoplanets are made of, how their atmospheres work, how their magnetic fields behave, and whether they could support conditions relevant to life, depends on assumptions about ice giant interiors that are drawn primarily from our understanding of Uranus and Neptune. If that understanding is wrong, If Uranus is rock-dominated rather than ice-dominated, the implications ripple outward through every exoplanet model built on the ice giant template. Consider the scale of this problem. The Kepler mission alone identified thousands of confirmed exoplanets, and the statistical analysis of that data set revealed that sub-Neptune worlds are the most abundant planet type around Sun-like stars. Roughly 30 to 50% of Sun-like stars host at least one planet in the sub-Neptune size range. The TESS mission has continued to expand this census. The James Webb Space Telescope is now characterizing the atmospheres of some of these worlds, detecting water vapor, carbon dioxide, and other molecules that hint at their internal compositions and atmospheric structures. But every interpretation of those atmospheric detections relies on models. When Webb detects water vapor in the atmosphere of a sub-Neptune world, the question of whether that water is a thin atmospheric component above a rocky surface or the evaporated outer layer of a deep water mantle depends on interior structure models. And those interior structure models are calibrated against the ice giants. If Uranus turns out to be rock-rich rather than water-rich, the models calibrated against it would need fundamental revision. Atmospheric detections that currently suggest water-rich interiors might instead be consistent with rocky worlds that have thin, volatile envelopes. Planets we currently classify as mini-Neptunes might turn out to be something entirely different. The chain of inference runs from the interior of one planet in our solar system to the classification of thousands of worlds across the galaxy. That is how much weight rests on the question of what Uranus is actually made of. And that is why the December 2025 study landed with such force in the planetary science community. It did not simply offer a new model, it demonstrated that the existing models were built on assumptions that the data does not actually support. The phrase ice giant, used in thousands of scientific papers and every popular description of the outer solar system, may be fundamentally misleading. The Voyager 2 radiation data adds one more layer of unreliability to the already thin foundation. The 2025 study from the Southwest Research Institute showed that the spacecraft likely encountered Uranus during a co-rotating interaction region, a solar wind structure that temporarily supercharged the magnetosphere and produced electromagnetic waves of extraordinary intensity. The strongest detected during Voyager 2's entire multi-decade mission. These waves, scientists now understand, can accelerate electrons to extreme energies rather than scattering them away, as was assumed in 1986. The radiation environment Voyager measured was probably transient, a storm-driven spike rather than a steady-state condition. This means our only close measurement of Uranus's radiation belts, one of the primary constraints on the magnetospheric dynamics that connect the interior to the space environment, may not represent normal conditions. We were looking at the planet through a distortion. We built models on that distortion, and we have had no way to check those models against a calmer, more representative dataset, because no other spacecraft has ever been there. Every thread of evidence about Uranus leads back to the same conclusion. We do not have enough data. The planet is genuinely, structurally strange, stranger than any single fact or headline can convey. But the full depth of its strangeness is hidden behind an information deficit so severe that it would be considered unacceptable for any other major planet in the solar system. Mars has multiple active orbiters and surface missions operating right now. Jupiter has Juno, Saturn had Cassini for 13 years. Uranus has 40-year-old data from a 5.5-hour flyby that happened during a solar storm. The magnetic field is wrong. The heat budget is wrong. The composition is unknown. The radiation environment was measured during an anomaly. The atmosphere was photographed during a seasonal extreme. And every one of these unknowns interacts with the others in ways that prevent scientists from resolving any single one in isolation. What emerges from this picture is not a planet with one interesting quirk. It is a planet whose entire physical character seems to operate outside the boundaries that every other world in the solar system respects. And the final question, the one that everything in this story has been building toward, is what that means. Not just for Uranus, but for the idea of a planet itself. For the assumption that the worlds in our neighborhood are familiar. For the quiet confidence that we understand the solar system we grew up in. That is where the story ends, and the answer is less comfortable than most people expect. There is a quiet assumption most people carry about the solar system. It runs so deep that they never articulate it, never examine it, never notice it is there. The assumption is that we know this place, that the 8 planets orbiting our star are understood objects, that whatever mysteries remain are details, footnotes, loose threads at the edges of a fabric that is otherwise complete. Mars might still surprise us with a microbe, Jupiter's moons might harbour oceans worth investigating, but the planets themselves, their structures, their behaviours, their basic physical characters are known quantities. We learned them in school, we have seen the pictures. The story is mostly told. Uranus dismantles that assumption one layer at a time. Not because it has one strange feature. Every planet has something unusual about it. Mercury's orbit precesses in a way that required general relativity to explain. Venus rotates backward. Mars has a volcano 3 times the height of Everest. Jupiter generates radiation belts that could kill an unshielded human in minutes. Saturn's density is low enough that it would float in water, if you could find a bathtub large enough. Neptune's winds are the fastest in the solar system. Oddities exist everywhere. What makes Uranus different is that the strangeness is not a feature. It is the architecture. The tilt is not a quirk bolted onto an otherwise normal planet. It is the organizing principle from which nearly everything else follows. The seasons are extreme because of the tilt. The atmospheric behavior is alien because of the seasons. The thermal deficit is connected to whatever event caused the tilt. The magnetic field is misaligned with the rotation in a way that may reflect an interior reshaped by the same event. The interior composition is unknown in a way that other planets' compositions are not. Partly because the planet's formation and impact history created a structure that does not fit standard models. And the information deficit, the staggering lack of data, persists partly because the very blandness the tilt produced during the Voyager encounter convinced a generation of scientists and policymakers that the planet was not interesting enough to revisit. Each piece of strangeness feeds the next. The tilt created the seasons. The seasons created the visual blandness at solstice. The blandness created the perception of boredom. The perception of boredom reduced scientific and public interest. The reduced interest meant fewer missions, less funding, less attention. And the less attention Uranus received, the longer its genuine mysteries went unresolved, which in turn reinforced the impression that there was nothing to resolve. It is a feedback loop of neglect, and it has left us in a position where one of the 8 major planets in our own solar system remains, In 2026, more poorly understood than many objects that are far more distant and far less accessible. This is not a comfortable realization. It forces a reckoning with something that the human relationship with space tends to avoid. We do not explore proportionally to what is important. We explore proportionally to what is dramatic. Jupiter is dramatic. Its storms are photogenic. Its radiation environment is menacing. Its moons hint at biology. Saturn is dramatic. The rings are the single most visually stunning structure in planetary science. Titan has lakes. Enceladus has geysers. Mars is dramatic in the way that all frontiers are dramatic, a place where humans might one day stand, which gives it an emotional gravity that no amount of scientific priority can override. Uranus is not dramatic in any of these ways. It does not photograph well. It does not have an obvious connection to the search for life. It does not evoke the frontier mythology that drives public enthusiasm for Mars, and its name ensures that any attempt to generate popular excitement is immediately undercut by the same joke that has followed the planet for decades. But drama is not the same as importance. And the importance of Uranus, the reason planetary scientists have spent years arguing that it deserves a flagship mission, extends far beyond the planet itself. The 2022 Planetary Science and Astrobiology Decadal Survey, the document that sets NASA's scientific priorities for the coming decade, ranked the Uranus orbiter and probe as the single highest priority new flagship mission for the period 2023 to 2032. Not Mars, not Europa, not Enceladus, Uranus. That ranking was not a gesture of pity toward an overlooked world. It was a scientific judgment that the questions Uranus can answer are among the most consequential in planetary science right now. The reasoning begins with what we covered earlier. Uranus and Neptune are our closest analogues for the most common type of planet in the galaxy. Sub-Neptune worlds outnumber every other planetary category around Sun-like stars, and every model of what those distant worlds are made of draws on our understanding of ice giant interiors. If that understanding is built on unjustified assumptions, as the 2025 Zurich study demonstrated it may be, the entire framework for interpreting the most abundant class of exoplanets needs revision. A single orbiter and probe at Uranus would not just resolve questions about one planet. It would recalibrate the models used to classify thousands of worlds across the Milky Way. That is the scientific case. But the scientific case, as compelling as it is, does not fully capture why Uranus matters. There is a deeper reason, one that is harder to quantify and easier to feel. Uranus matters because it is a test of whether we take our own solar system seriously. We talk often about exploring the unknown. We celebrate missions to distant worlds. We invest billions in telescopes that peer across the universe to study galaxies billions of light years away. And we should. Those investments have returned extraordinary knowledge and will continue to do so. But there is something dissonant about reaching for the edge of the observable universe, while leaving a giant planet in our own system fundamentally unexamined. It is as though a family spent decades and enormous resources studying houses on the other side of the city, while never once opening the door to the room at the end of their own hallway. The room is right there. It has always been right there. And the reason nobody opened the door has more to do with a vague feeling that the room is probably boring than with any actual assessment of what is inside. The Uranus orbiter and probe, if it is built and launched, will change this. The original mission concept targeted a launch around 2031. using a Falcon Heavy or equivalent launch vehicle, with a gravity assist at Jupiter allowing arrival at Uranus around 2044. Budget pressures and delays in plutonium production have shifted the likely launch window to the mid to late 2030s, which means arrival would not occur until roughly the mid 2040s at the earliest. Those numbers are sobering. A child born today will likely be in their 20s before the spacecraft arrives. The scientists who wrote the decadal survey recommendation will be decades further into their careers or retired by the time the first orbital data comes back. The pace of outer solar system exploration is measured in generations, not news cycles. And the decisions being made right now in this decade about whether to fund the mission, how to design it, and when to launch it will determine whether humanity gets its second look at Uranus within the lifetime of anyone currently alive. The mission, as currently envisioned, would carry an orbiter that would spend several years in the Uranian system, mapping the gravitational field with enough precision to break the interior composition degeneracy, characterizing the magnetic field and its interaction with the solar wind over an extended period, studying the atmosphere and its seasonal evolution, and examining the moons and rings in detail. An atmospheric probe dropped into Uranus's atmosphere would descend through the cloud layers, directly measuring composition, temperature, pressure, and wind speed as a function of depth. That probe would provide the first in situ measurement of what the atmosphere of an ice giant is actually made of, resolving questions that remote sensing alone cannot answer. And the moons themselves may hold surprises that rival anything the planet can offer. This is a dimension of the Uranus story that most people have never encountered. When Enceladus was revealed by Cassini to be an active ocean world spraying water ice into space from a subsurface sea, nobody had predicted it. When Europa's ice shell was confirmed to cover a global saltwater ocean, it reshaped the search for life beyond Earth. The lesson from both discoveries was the same. Small icy moons in the outer solar system can hide liquid water oceans maintained by tidal heating. And those oceans can persist for geologically long periods, even billions of miles from the sun. The Uranian moons have received a fraction of the attention devoted to their Jovian and Saturnian counterparts. But recent modelling work has suggested that at least two of them, Ariel and Miranda, may have experienced significant tidal heating in the past and could potentially harbour subsurface liquid water even now. Ariel, the brightest and one of the geologically youngest of the major Uranian moons, shows surface features that point to relatively recent resurfacing. Its terrain includes smooth plains that appear to have been flooded by material welling up from below, flow features consistent with cryovolcanism, the eruption of water or water ammonia mixtures onto an icy surface, and a network of fault valleys that suggest the interior has been tectonically active within the last billion years, or possibly more recently. For a moon orbiting a planet that most people assume is geologically dead, this is a striking set of clues. Miranda, despite its tiny size, adds to the case. The same extreme surface geology that makes it visually dramatic, the cliff faces, the jumbled terrain, the patchwork of young and ancient surfaces requires an energy source. That energy most likely came from tidal interactions with other moons and with Uranus itself, interactions that may have been stronger in the past when the orbital resonances were different. Whether any of that tidal energy persists today, and whether it is sufficient to maintain liquid water at depth, are open questions that cannot be answered without a dedicated orbiter making close flybys with instruments designed to detect subsurface oceans through magnetic induction measurements or ice-penetrating radar. The possibility, even if it remains unconfirmed, that the Uranian system harbors its own ocean worlds is a quiet revolution waiting to happen. If an orbiter were to detect evidence of a subsurface ocean on Ariel or Miranda, it would mean that ocean worlds are not confined to the systems of Jupiter and Saturn. They would extend to the ice giant realm, to a region of the solar system that has never been explored in any meaningful depth. The implications for habitability, for the distribution of liquid water in the cosmos, and for where we look for life would expand overnight. Additional mission concepts have emerged alongside the NASA flagship proposal. The European Space Agency has studied a concept called MUSE, which mirrors the orbiter and probe architecture. China's Tianwen-4 mission, currently in development, includes a Uranus flyby as part of a broader outer solar system mission. A concept called KAIS-MIUS, presented in 2026, proposes a dedicated 2-spacecraft mission to study Uranus with complementary instrument suites. The international interest is genuine and growing. Uranus is no longer a planetary afterthought. It is becoming, slowly, the next frontier. But the gap between now and the arrival of any of these missions is measured in decades. And in that gap, the James Webb Space Telescope is the only instrument capable of making significant new observations of the Uranian system at high sensitivity and resolution. Webb has already delivered results that shifted the scientific conversation. The ionosphere mapping, the moon discovery, the atmospheric monitoring, all of these have come from a telescope that was not designed primarily for solar system science, but has proven extraordinarily capable of it. Webb's observations of Uranus will continue throughout its operational lifetime. Each observation adds another piece to a puzzle that has been data-starved for 40 years. But even Webb has limits. It cannot measure the gravitational field. It cannot drop a probe into the atmosphere. It cannot orbit the planet and watch it change over seasons and years. The fundamental questions about Uranus's interior, its thermal evolution, and its magnetic dynamo require a dedicated mission. Webb is the bridge. The orbiter is the destination. Now step back from the specifics and consider what Uranus, taken as a whole, has revealed about the nature of planets. We organize the solar system into categories: rocky planets, gas giants, ice giants. These labels are useful shorthand, but they carry an implicit promise that the members of each category are broadly similar. Rocky planets are dense, small, and have thin atmospheres or none. Gas giants are massive, hydrogen-dominated, and have powerful magnetic fields aligned with their rotation. Ice giants are medium-sized, volatile-rich, and colder versions of the gas giants. Uranus fits none of these descriptions comfortably. It is classified as an ice giant, but it might be made of rock. Its magnetic field is not aligned with its rotation by any reasonable definition of aligned. Its thermal behavior is unlike any other giant planets. Its atmosphere goes dormant for decades at a time in a way that no other giant planet's atmosphere does. Its seasonal cycle is so extreme that it has no parallel anywhere in the solar system. Its interior may be stably stratified rather than convective, which would make it structurally different from every model of giant planet interiors that has been developed over the past half-century. Uranus does not break one rule. It breaks the category. It suggests that the neat division of planets into a handful of types is a convenience, not a truth. that the real landscape of planetary possibility is wider, stranger, and less orderly than the textbook taxonomy implies. And if that is true for a planet in our own system, a planet we have been staring at for 245 years, what does it say about the thousands of worlds we've discovered around other stars and the billions we have not yet found? This is the thought that sits at the center of the Uranus story. The thought that transforms it from a tale about one overlooked planet into something that touches the foundations of how we understand worlds in general. Familiarity is not understanding. The fact that we can point to Uranus on a chart, that we know its orbital period and its approximate mass and the number of its moons, does not mean we understand it. Understanding requires knowing what it is made of. It requires knowing how its interior works. It requires knowing why its magnetic field is shaped the way it is, why its heat escapes so slowly, why its atmosphere responds to seasons the way it does, and what the giant impact, if it happened, actually did to the planet's deep structure. We have none of these answers. We have hypotheses, models, educated guesses, and a slowly growing pile of remote observations that constrain the possibilities without eliminating most of them. And if that is the state of our knowledge about a planet 1.8 billion miles away, a planet we can observe with telescopes any clear night, a planet we have already visited once, what is the state of our knowledge about anything further, anything smaller, anything harder to see? Uranus is a mirror. It reflects the limits of human attention. It reflects the tendency to mistake a first impression for a final verdict. It reflects the assumption that if something does not look interesting at first glance, it probably is not interesting at all. And it reflects the cost of that assumption. 4 decades of a planet sitting in the dark, waiting for someone to come back with better instruments and a longer attention span. The comparison with other planets is instructive in a way that cuts deeper than simple resource allocation. When Cassini arrived at Saturn in 2004, it completely transformed our understanding of the Saturnian system. Before Cassini, Titan was a hazy orange mystery. After Cassini and its HOY GENS probe, Titan was a world with methane rain, hydrocarbon lakes, and a subsurface ocean. Before Cassini, Enceladus was an unremarkable icy moon. After Cassini, it was a world with active geysers spraying water from a subsurface ocean into space, one of the most promising environments for extraterrestrial life in the solar system. None of this was expected. None of it was predicted in advance. It was discovered because someone sent a spacecraft and gave it time to look. Juno has done the same for Jupiter, revealing an interior structure more complex and less orderly than models predicted, with a dilute core that may extend through a large fraction of the planet, rather than a compact, dense ball at the center. Before Juno, the textbook picture of Jupiter's interior was simple. After Juno, it is not. The mission did not confirm what we thought we knew. It replaced it with something stranger and more nuanced. Every flagship mission to a giant planet has done this. Every single one has returned results that force significant revision of prior understanding. There is no reason to believe a Uranus mission would be different. There is every reason to believe it would be more transformative, precisely because our starting knowledge is so much thinner. The unknown is not distributed evenly across the solar system. It is concentrated at Uranus. It is pooled there, deep and dark and waiting. And the planet does not make it easy to care, because it does not perform for the cameras, does not hint at biology, does not carry the romance of the frontier. It simply sits, tilted sideways, turning slowly in the cold, holding answers to questions we have not yet found the will to ask properly. There is a version of this story that ends with a call to action, a plea for funding, a campaign for a mission. That is a legitimate ending, and others have written it well. But the ending that feels most honest is quieter than that. The most unsettling thing about Uranus is not its tilt. It is not the magnetic field or the missing heat or the compositional uncertainty. It is the realization that the strangest planet in the solar system has been right there, inside our own planetary family, for the entire history of human civilization. We discovered it 245 years ago. We visited it once. We glanced at it. We saw a featureless blue disk. And we moved on. We moved on, and in doing so, we told ourselves a story about what was worth paying attention to. Jupiter is worth paying attention to because it is massive and violent. Saturn is worth paying attention to because it is beautiful and its moons might harbor life. Mars is worth paying attention to because we might go there someday. These are true statements, but they contain an unstated corollary. Uranus is not worth paying attention to because it is none of those things. And that corollary, that quiet dismissal, is the most human thing in this entire story. We're a species that allocates attention based on spectacle. We're drawn to the dramatic, the photogenic, the emotionally immediate. A planet that responds to scrutiny by revealing deeper and deeper layers of strangeness, but does so quietly, without visual fireworks, without a clear connection to human ambitions, without even a name that can be spoken in a classroom, without triggering laughter. That planet falls through the cracks of human interest. Not because it deserves to, because our filters are miscalibrated. Uranus is the proof that planetary familiarity is an illusion. We do not understand the solar system as well as we believe we do. We understand the part of it that we have looked at carefully, and we have looked at Uranus for a total of 5.5 hours from close range, under abnormal conditions, with instruments from the 1970s, and then declared, through decades of inattention, that we had seen enough. We had not seen enough. We had barely seen anything. The seventh planet from the Sun orbits in near silence, tilted on its side, wrapped in an atmosphere that smells of rotten eggs, generating a magnetic field that emerges from the wrong place at the wrong angle, hiding an interior that could be made of ice or rock, and we cannot tell which, cycling through seasons that last longer than most human careers, cooling at the top while retaining subtle warmth at the bottom, carrying 29 moons that may conceal oceans of their own, and a dark ring system, and 4.5 billion years of unexamined history. It is the strangest planet in the solar system, not because it has one unusual feature, because its entire physical character is built around violating the expectations that every other planet taught us to hold. It is a world that does not work the way worlds are supposed to work. And the fact that it has been sitting there, this close, this overlooked, this profoundly misunderstood, for this long, says something not just about Uranus, but about the species that chose to look away. The next time someone makes the joke, the easy one, the one that has followed this planet for decades, let it land. And then consider what is actually out there, rolling sideways through the dark, waiting for someone to take it seriously. It has been waiting for a very long time,